the material that we've covered so far since exam 2. So that would be lectures 24 to 34. Looking back at the schedule, that starts with SNOT loads, right, and ends with approximate analysis, so the portal method that we just finished covering. And, a lot of this is repeated from before, right, stuff that has been applicable to previous exams. It also applies to this exam. The main difference is that this exam is open note. So you're allowed to bring any notes, anything that's a hard copy except for books, right? No, the textbook is not allowed just because not everybody has a textbook as a hard copy. So keep that in mind. However, the note that I wrote in red is worth emphasizing here. I still highly recommend that you treat this as you prepare for the exam. Treat it as though it were a closed note, a closed book exam, and write, 1 to 2 to 3 page, however, whatever you think you need, note sheet. You can use your previous note sheets for exam 1 and 2 material, and then create a new one for exam 3 material, right? Have that as a quick and easy reference for you, and then have your organized notebook for, anything that you may have forgotten or missed, okay? So down here, right, you can see, as before, a few notes on the items that will be the new material that's focused, that this exam is going to cover through approximate analysis. So do you have any questions for me on the exam? Okay. All right, so going back to the schedule then, today we will have a lecture that focuses on defining failure mechanism of plastic hinge. So we're going to demonstrate and show you how plastic hinge can form, and then what that means as far as failure goes. And this will tie into the final project. So really the first part of today's lecture will be focusing on the plastic hinge, and then we're going to get into some project-specific things. Now, the project itself, I will have posted for you no later than Wednesday before class. So Wednesday during class is when I will be presenting that information to you, what the final project is and what you're expected to do. But just as a primer or for some background information in the context of today's lecture, you'll be analyzing a frame, right? So I talked about this already a little bit. So you're going to be given a building that is constructed using a moment frame system, okay? And you're going to be tasked with analyzing a single interior frame, right? So just a 2-dimensional analysis. You don't have to worry about the whole 3-dimensional building, even though it will be presented to you as a 3-dimensional building. But you're going to need that information to figure out what the loading will be, right? Because you'll be given the loading, the dead and live loads in pounds per square feet. You'll be given wind loads as point loads. We'll talk more about that on Wednesday. And then you're going to conduct vertical analysis, approximate analysis that is, on the frame to evaluate what are, the stresses that you expect to result from those vertical loads. And you'll conduct a portal analysis for the wind loads, right? And then you will superimpose those approximate analysis results to obtain a total expected set of forces that would be acting on beams and columns within that frame. Once you have that information for every single beam and frame, or beam and column in that one frame, then you're going to work with that to identify which one will be the most severely loaded, and then you're going to use that information to inform your design. So we'll talk more about that on Wednesday, but that's just a little bit of a background for the context of today's lecture. All right, so before we launch into this, as a reminder, homework 10 is due Wednesday, right? And I have provided you with the solution to that assignment. So homework 10 will be graded largely based on completion and effort and presentation. So, still make sure that you give yourself plenty of time to work through it. And remember, the idea is that you have a chance to practice the portal method with results to check your work against before you apply it to the final project. Do you have any questions for me on homework 10? Okay. All right. Yes.
Homework 10 stuff isn't on the exam, right? Or is it?
It is. Okay. Yes. Yeah. So everything through approximate analysis is on the exam. All right. So introducing the concept of plastic hinge. You are familiar with this stress-strain curve from mechanics of materials. So this is what's shown here is very much an idealized stress-strain curve, right? Because it's not going to be a perfectly, a single point transition to a perfectly linear plastic range, right? The plastic range is generally nonlinear, and it'll look something like that depending on the material. So we'll note here that this is idealized. And it's idealized to represent a ductile material. A ductile material is one that will be able to undergo significant plastic deformation before it fractures or fails, right? So do you remember that discussion of brittle materials versus ductile materials in mechanics of materials? I see some nods. Okay. Yeah, so a brittle material would likely fail shortly after yield, but a ductile material will have a long life in the plastic region. What's an example of a ductile material?
Steel.
Yep, steel is a ductile material. Now, as you can see, right, the material will be elastic until the stress reaches yield, and then that's when it enters the plastic range. And we'll do a little recap on mechanics here. So if we consider a beam that has a solid rectangular cross-section as shown, I'm going to go ahead and note axes. Over here, we'll say the longitudinal axis is the x-axis. The transverse axis is the y, and the other transverse axis is the z. So this distance c represents the distance from the neutral axis to the extreme fibers. And the moment of inertia would be the width b times the height, which is 2c cubed over 12, which comes out to 2/3 times bc cubed. Now, if we apply a moment to this cross-section, right, and increase that moment until the extreme fibers reach that yield stress, then we have the stress distribution as shown here, where we have zero stress at the neutral axis and a maximum stress equal to the yield stress at the two extreme fibers, right? So one side will be in tension while the other side is in compression. And for a positive moment, as shown there, it would be the top that's in compression and the bottom that's in tension. So your moment, right, when it's equal to, we call that moment that causes yield in the extreme fibers. We call that the yield moment because this state represents the onset of yield. All right, so you see this noted as my to denote that it's the yield moment. So I'll note here, this is the value of moment that causes initial yield. And as you know, the relationship between moment and stress comes from the moment of inertia, I, and then the distance to the point where you're calculating stress, right? So in this case, since we're considering the extreme fibers having just yielded, we can relate that to our yield moment by noting our yield stress at those extreme fibers times the moment of inertia divided by c, which is that distance to the extreme fiber. And then plugging in this expression for moment of inertia, we would get our yield moment in terms of the yield stress and the cross-section dimensions b and c. Now, if we continue to increase the load so that that moment increases beyond my, then more of the fibers within the cross-section will begin to yield, right? So it's not just the extreme fibers anymore, but now the closer and closer you get to the neutral axis, more of those fibers will be yielding. So our stress distribution begins to take on a plateau. All right, so we have this yield plateau, and then we have the portion that is linearly decreasing to 0 at the neutral axis. Now in this scenario, all right, moment is greater than the yield moment, but how much of that portion has yielded depends on how much, or it depends on where this moment is between the yield moment and what we call the ultimate moment. All right, so the ultimate moment is that moment that would cause every single fiber within the depth of the cross-section at that location, right, along the length of the beam, to reach the yield stress. And so in an advanced course, you would be able to analyze this scenario more in depth, right, and be able to figure out exactly where this point is, where the yield plateau ends. But in this class, we're not going to dive that deep, so we're just going to kind of skip ahead to the ultimate failure scenario. And in that case, you have a constant stress distribution due to bending, right? So your moment is the ultimate moment. Every single fiber within the depth of that cross-section has reached yield. And so your resultant forces associated with that stress distribution, right? You still have compression in the top half and tension in the bottom half. So those resultant forces cancel each other out. You still have no net axial force on the cross-section, right? So that will always be true due to bending. Due to bending, there is no net axial force. And so then you have your ultimate moment in terms of the yield stress and the cross-section dimensions shown here. All right, so that's just saying that's equal to stress times the area over which it acts times the moment arm. And in this case, that moment arm is equal to C because that is the distance between the force couple, right, of the resultant forces. Now, at that location where ultimate moment has been reached and the entire cross-section has reached the yield stress, then that section will behave like a hinge, right? And that's what we call a plastic hinge. So since every single fiber along the depth in that location has reached the yield stress, it's no longer an elastic material, right? So it can no longer transfer moment beyond that ultimate moment value. Now, there is a relationship between the ultimate moment and the yield moment, right? And I mentioned earlier that if you're examining this scenario, how much of the plateau has, or how much of this section has yielded depends on where this moment is between the yield moment and the ultimate moment. And the ratio between these two values depends on the cross-section shape. So for rectangular cross-sections, the ultimate moment is equal to 1.5 times the yield moment, all right? So that's standard for any rectangular cross-section, if it's a solid rectangular cross-section. If you have an I-beam, your ultimate moment, it depends on the exact I-beam dimensions, but it's going to be approximately 1.2 times the yield moment. All right, so this difference means that for certain cross-sections, all right, there is a closer margin between yield and total collapse compared to other cross-sections. So this is, again, just some background information for you. And to emphasize a few other things here, right, so at the location where the ultimate moment is reached, by that I mean the location along the length of the beam, all right? And when we talk about I-beams, right, the most common example of an I-beam is those wide flange sections or W sections. So you had a little bit of exposure to working with W section designations in homework 2. So remember, if you have, for example, a W12 by 10, that means it's approximately 12 inches deep and the weight is 10 pounds per linear foot. So remember that, how that designation works. We're going to be working with these sections again in the final project. So once that document is released, you will see it's going to have several pages of tables attached to it. Those tables are going to be a bunch of different wide flange sections that you'll have to choose from for your final project design. All right, so we'll go through a quick example just to illustrate this plastic hinge, how it can lead to collapse, right? And demonstrate that, certain beams will need to develop more than one plastic hinge before they fail. So if you have a determinate beam, you only need one plastic hinge to form before it fails, right? If you have an indeterminate beam, one plastic hinge forming is not enough. One plastic hinge forming will just change it to, if it's 1 degree indeterminate, it'll change it to a determinate beam, right? So you need to have as many plastic hinges form to reach failure as there are degrees of indeterminacy plus 1. And so in this example, we'll look at a beam that is 1 degree indeterminate, right? Fixed at the left and a roller at the right. Applied load acting at the center of the span. If we conduct a simple elastic analysis, all right, and we could do this, for example, using the finite element method to obtain these reaction forces, we can translate then those reaction forces into our shear and moment diagrams. So we would have shear and moment diagrams that look like this. So you can see that the maximum moment will occur at the fixed support. All right, and so that means that as you increase this applied load, the plastic hinge will first form at the fixed support. All right, and the next location where the plastic hinge will form is right underneath the applied load. And we can see that because that's the other peak point on our moment diagram. So if we increase that load to form the first hinge, this beam will still be stable. Right? then that is effectively changing that fixed support to a pin support, right, with a moment equal to the ultimate moment applied at that location. And that moment will act in the direction that will try to restore the beam to its original position, right? So it's working against the way that the beam wants to deflect. The moment diagram then, right? So it's not as simple as determining an elastic moment for a simply supported beam, right? Because you have this ultimate moment at that fixed end with a plastic hinge. So your moment diagram will look like this now, where you have reached that ultimate moment at the fixed end, and then the moment at the location where the load is applied is slightly less than that ultimate moment, right? So this plastic hinge has formed 5/6 of the way, right? But not fully. Continue to increase that load until you have reached ultimate moment at that location, that second location. Then you have formed the second hinge, and once both hinges have formed, then you have collapse. And now your free body diagram would look something like this, right, with the collapsed position, and you have ultimate moment working at both locations. Your moment diagram would then look like this. So in an advanced class, we would be able to apply this method to evaluate different possible collapse scenarios. In this case, this is the only collapse scenario that makes sense. In other situations, there might be other collapse scenarios that you would have to investigate a little more closely to determine whether they are the true mechanism of collapse or not. And again, that's something that you can experience in advanced courses if you choose to take them. But for now, we will move on and start zeroing in on things that will be directly relevant to your final project. So the plastic hinge, that's mainly background information. You don't have to actually go through any of that analysis for your final project, right? So that's just to expose you to how that kind of failure occurs. In your final project, you will be asked to analyze, as I said before, the beams and columns in a two-dimensional frame. And so we have talked about how to conduct approximate analysis due to vertical loads in a frame, right? And we've talked about how to conduct approximate analysis due to lateral loads in a frame. So now I'm going to show you how to approach this for your final project, and then we'll look at how to combine that information from the two separate analyses. All right, so your preliminary analysis for your final project, all right, you'll have the portal method to apply, and that's going to provide shear, moment, and axial forces in all members, right? So remember, as you go through the portal method, you're going to get axial force in your beams and your columns, shear force in your beams and your columns. And then from the shear forces, you're going to calculate what those end moments are, right? So, and remember that this is only applicable for horizontal loads. So even if you have vertical loads present, which you will in your final project, you will ignore them for the portal method, right? So no vertical loads on the portal method. All right, and in your final project, those horizontal loads are specifically wind loads. Now, the vertical loads that you'll be dealing with include dead, live, and wind. All right, so we got a flat roof. So remember, we can have wind pressures on that roof acting upwards. So let's think about the columns in this frame. All right, the axial forces in the column are going to come from the dead loads, live loads, and wind loads. In your project, I'm already lumping the wind loads together as a point load that's applied to the column, all right? So you don't have to worry about wind loads on beams, all right? So beams, you only have to think about dead and live loads. This is a conservative simplification, all right, because your wind loads are acting in the opposite direction and would counter the effects of dead and live loads. But by the time they get to the column, right, it's going to be a little bit more significant of a magnitude than it is for the beams. So it's worth kind of incorporating into your column analysis to reduce that axial load a bit in your columns to help lighten the load, right, lighten the design load. So that's the reasoning behind why I'm only asking you to think about wind for the columns. So I'll note here that that is only going to affect the columns. All right, and then you'll have a line load that includes the dead and live loads on your roof, and then you'll have line loads for the floors, all right, for dead and live. And so those line loads, the units should be in pounds per foot or kips per foot, right? You can choose either of those. All right, so let's think about the axial forces in the column. All right, essentially what you're going to want to do is cut through the columns, all right, make a cut. So you're exposing the internal axial force in each column. So I've got the free body diagram for columns 4, which is this top one here, and column 3, which is the middle, the bottom middle one there. All right, so after you cut through the column, you want to use the tributary width and apply statics. All right, so for this column, column 4, the tributary width is going to be half the distance to the two columns on either side, all right? So here I've noted this as L1 and L2. So the tributary width is included in this free body diagram, half of each of those lengths. And then the internal force that is exposed in that column is going to be equal to the distributed load W1, all right, so that's your dead and live, times the distance over which it acts, which is half of L1 plus L2. And then we're going to subtract that wind load, right, to obtain the axial force in that column. Then when we go down to the level below, right, we can either cut through that column and look at everything above it and do the same thing, or, right, I'll write that out first and then I'll show you the alternative. So that would be our loads on the roof plus the loads on the floor times the distance over which they act, which is half of L1 plus L2 minus the wind load. Or we can say P3 is equal to P4, which we just calculated, plus the load on the floor, W2, times half of L1 plus L2. All right, so whatever makes more sense to you. It's worth noting that if you apply one method, it's worth at least spot checking and, maybe use the other method to kind of gut check your calculations, right? So in that manner, you can go and determine the axial forces in the columns throughout that frame, because that's the only thing that we didn't really cover in the approximate analysis method for vertical loads on frames, right? We looked at beams, we focused on beams for that method. So now you've got the columns sorted out on that. And we're going to, and this is another simplification, but it's a reasonable simplification for the most part. In your project, we're going to ignore the effects of vertical loads on shear and moment in the columns, right? So in your project, the shear and moment in columns is only going to come from the portal method, your lateral loads. All right, so now for beams, all right, this is a recap. We've already seen this method last 2 weeks ago, right, last time. So you'll have your frame approximation where you're treating it as a beam that has fixed ends with an inflection point at 0.1 L from either end. And at that inflection point, right, you can treat it as a hinge and use that to determine the maximum moment. And then you can figure out the end moments as well from that. So you'll have a moment diagram for every single beam. All right, that will look something like this. All right, where you have a value that is your maximum positive moment, and then you'll have your maximum negative moment value. So those are the pieces of information that you are going to need to record for the superposition portion of the project, all right? And now I'll talk a little bit about that. So let's talk about the beams first. With the beams, all right, from vertical loads, we looked at moment diagrams, right? Vertical loads on beams aren't going to really affect the axial forces. So for the beams, the superimposing of results is going to only be relevant for moment diagrams. So you're going to have a moment diagram that's linear from portal method, all right? So I'm going to I'll say this is, all right, lateral, and then vertical. So you're going to have a value that is the left side from the lateral loads. All right, you're going to have a value that is the right side for lateral loads. And then the center value will be 0 from your lateral loads. Right, because remember in the portal method, we assume that the hinge occurs exactly in the middle of each beam and column. And for beams, that is pretty accurate. So center point will always have 0 moment in your beams from the lateral loads. From the vertical loads, you're going to have a value on the left and a value on the right and a value in the center. So for your superimposed moment diagram, all right, and this is what I want to see in your final project, get the values from these 3 points, right, left, right, and center, and then plot them and connect them with a quadratic equation, right? So it's going to be roughly quadratic. You're adding a linear to a quadratic. So don't worry about having a perfect moment diagram, but I do want to see these 3 points represented accurately. So you'll have the left side from your lateral plus the left side from the vertical, and so on. All right, and this one, the lateral value is going to be 0, so your center point is just going to come from the vertical load. And then you're going to end up with something either like this, where your left end moment is going to be a negative value that's smaller in magnitude than your right end moment, or you're going to end up with a moment diagram where your left end moment is a net positive value and your right end moment is a negative net value, right? So keep it in mind that you could have either one of these two results. Now for the columns, since I just said that we were going to neglect the effects of vertical loads on shear and moment in your columns, that means that the shear and moment in your columns will come only from the portal method, right? Similar to how the axial forces in the beams are only coming from the portal method. And so with the columns, the superimposing of results is only relevant for axial forces, right? So the axial forces from the portal method will be combined with the axial forces that you found from the vertical loads using this method up here. And I'll just note that right here, your moment being equal to V times H over 2, right? That is from the portal method. And you're going to end up with a moment diagram if you have fixed base columns that looks something like that, right? Where you have counterclockwise moments on both ends. So over here, I'm going to write a quick summary of this approach. All right, so for columns, you're going to have axial force from vertical loads, and from lateral loads, you're going to have axial, shear, and moment. And you want to superimpose the axial. Well, technically you're superimposing everything, right? But it's the axial forces that you're going to need to actually do some math on. For the beams, you're going to have moment from the vertical loads, and you're going to have axial, shear, and moment from lateral loads. And when you apply the superimposing of loads, that's going to be the moment diagrams. So then you'll want to keep track of the axial force in the moment is what you're ultimately interested in for every single beam and column, all right? So talk a bit more about that in a moment. We're going to neglect the shear moving forward because really the only thing you need the shear forces for is to calculate the moment from the portal method, right? So to determine the maximum normal stress on an element, all right, and this kind of takes us back to the previous pages, all right? So remember, we're looking for the total, let's see, maybe I have it on the next page there. Oh yeah, all right. So I've got it on the next page for us. So I've got it sort of written out here as well as a teaser, all right? So you're gonna identify the maximum moment in each beam or column and also the maximum axial force, all right? So I'm gonna note that here, maximum moment and axial. And then you're going to find cross-section properties from the beam tables. And we'll go over how to do that on Wednesday. So the cross-section properties that you're going to be interested in are the cross-sectional area, and then this property called S, which is the section modulus. It's defined as the moment of inertia divided by the distance from the neutral axis to the extreme fiber, all right? So we'll get into more of that on Wednesday. But because the normal stress is going to be, it's going to have contributions from the axial force and from bending, right? Because your axial force on the column will cause a uniform normal stress distribution, and then your bending stress on the column or beam will cause a linear normal stress distribution where it's 0 at the neutral axis and extreme at the extreme fibers, if we're talking about being in the elastic region anyway. So your total stress calculation for an individual element is going to be the axial force divided by the cross-sectional area plus or minus the bending moment divided by this section modulus, all right? And so here is how I recommend you start to organize your results, or I highly recommend that you at least include something like this in your work at the superposition phase of the project. So listing every single member and then listing the axial force. You can include the shear if you want. You don't really need to. What's essential is the axial force and the moment. Right, and so this is just kind of another summary showing you that the axial force in the columns will come from lateral and vertical. For the beams, it's just going to be from lateral. And the moment in the columns is just going to be from lateral, whereas the moment in the beams will be from lateral and vertical. And remember that for the moment in the beams, you're going to have a value at the left end, the right end, and the center. And you're going to want to, for this table, all right, so for identifying the maximum moment in the beam, you're going to want the maximum magnitude. So I'll say use the maximum magnitude. Between those 3 points. So then for the preliminary design, you want to use the total force in a given beam or column. Your design criteria is going to be making sure that the calculated stress due to your approximate analysis methods does not exceed an allowable stress, right? So the allowable stress will be given in the project document. You cannot exceed that in any member. So, of course, the catch is that you need to know the section properties in order to determine what your stress is. And so how do you know section properties if you are trying to use the stress to find a size that will work? Well, this is where the iterative process of design comes into play. So we'll talk more about that on Wednesday with some examples, and what I'll do is I'll introduce the project first, and then we'll come back to this set of notes and go through some examples to show you that process. But down here, right, we can finish up this conversation today. This is a little review of normal stress from mechanics of materials, right? So over on this side, you have the axial stress. Sigma is equal to P over A, right? So if you have compression, we show that acting towards the section. If you have tension, we show that acting away from the section, right? So for bending stresses, right, similar. We have a positive moment causing compression at the top and tension at the bottom. A negative moment is the reverse. And in this equation, right, stress is equal to plus or minus my over I. All right, that's how you're familiar with it. Usually I say it's negative my over I because for a positive moment in the positive y direction, you want a negative result for your stress. Now we're going to introduce this section modulus, which is the moment of inertia divided by c, right, where c is that distance from the neutral axis to the extreme fiber. Specifically, we define c as being equal to half of the depth of the cross-section. And then my last note before releasing you today is that this y is a variable distance from the neutral axis in the equation. All right, so for the maximum stress, we will use the maximum value for y, which is going to be c. Questions? All right, we'll pick this up on Wednesday, and by then I will have posted the final project for you. So I'll see you then.